Hello everyone. In this session, we'll discuss transpose, conjugate and transpose conjugate of a matrix. With first one at as trace of matrix. Right? First of all, we'll find trace of a matrix only for a square matrix. So it has to be square matrix, right? And this trace, which is also given as TR for A if A is the matrix, is nothing but sum of the diagonal element for, I'll say, any square matrix, right? So that is trace A is equal to sum of Aij for I in the sense of all the values for I equal to j, right? So by I we mean all the possible sum, right? So for example, if we have 2 1 3 4 5 6 0 minus 1 7, a 3 cross 3 matrix A, then trace of A will be sum of the diagonal elements. So 2, 5 and 7. 2 plus 5 plus 7. So this is 14. This is the trace, right? Let's see the properties. The first property is, if we have two matrices for which we are finding the sum, obviously when the sum is defined, that means they have to be of the same dimension and obviously they have to be square matrix. We'll say that trace of A and trace of B is going to be same as trace of A plus B, right? A and B, like we are adding the matrices, so their traces will also be added. Next is trace of a matrix is same as trace of its transpose. We'll see what is transpose right after this topic. So it doesn't matter if the matrix has been transposed, but the trace will be same. Next is trace of AB is same as trace of BA. Again, when the multiplication is defined, obviously if these two are both the square matrices or the final product is square matrix, condition it is defined, the trace is going to be same, right? Next is whether you are finding trace of A transpose B or trace of A B transpose or trace of B transpose A or transpose of BA transpose. These are all going to be same. And likewise, if you are finding trace of maybe more than two matrices involved in the multiplication, unless you are not changing the order, you are going to get the same trace. So ABCD will be BCDA, same as trace of CDAB, and same as trace of DABC. So it is trace, you can say trace is invariant under cyclic permutation or arrangement. We have it in the same cycle, right? A, B, C, D, B, C, D, A, C, D, A, B, and D, A, B, C are all in the same cycle. And trace of AB is not equal to trace of A into trace of B. Won't be required, but we should know this, right? Let's see the next one. Next is transpose of matrix. Need not be a square matrix, so your matrix may not be square. It can be a rectangular matrix, any simple matrix. And for this transpose, it is obtained by interchanging rows and columns, right? So rows will become columns, columns will become rows, denoted as A transpose or maybe A dash. That is, if we have A of dimension m cross n, then transpose will give you A transpose, which is n cross m, because the number of rows and columns are interchanged. So number of rows will become n and number of columns will become m. And the elements, if it was Aij, it becomes Aji, right? Being interchanged. For example, if we have A equal to, suppose 1, 2, 3, 4, 5, 6. So this is a 3 cross 2 matrix. When transposed, A transpose will become, so you have 3 rows and 2 columns. So your column becomes your row. So this column 1, 2, 3 becomes your first row. 1, 2, 3, 4, 5, 6 is your second column, right? So let's see some of the properties. If you transpose a transpose, what will happen? We'll be interchanging the rows and columns, and then again we'll be doing the same thing. So being done twice, you'll get the same thing. So A transpose will give you the same matrix itself. And if we are transposing the sum, we can simply transpose the matrices and then add it, because this can be distributed. But if you are transposing a product, multiplication of a matrix, in order to distribute the transpose, you'll have to change the order. So AB transpose becomes B transpose into A transpose, or otherwise if it is A B C transpose, this becomes C transpose B transpose A transpose, right? Also, for diagonal matrix, let's say we had A equal to diagonal maybe A B C. Now where does this diagonal elements lie? Maybe it's like A11, A22, A33, likewise, right? So now we have seen that while we are transposing, what happens, as we said, Aij is replaced or exchanged with Aji. For example, A12 is replaced with A21, what about A11? A11 will be replaced with A11 itself, right? So the diagonal elements will remain at the same position, and ultimately A transpose will become same as the previous one, A, B, C. So you can say A transpose and A are same for the case of diagonal matrix, not in general, right? Let's see the next one. This is complex conjugate. We have seen what is complex number, we have seen what is complex conjugate for normal z, for z equal to x plus iy. We have seen this, we know this, z equal to x plus iy, then z conjugate becomes x minus iy. That is, the imaginary part is being multiplied with a factor of -1, right? So when we are doing a complex conjugate for a matrix, we need to complex conjugate each and every element of this matrix, and that is how it will give us the complex conjugate. This is generally represented by like z bar, similarly a bar. So this is obtained by complex conjugating each of the elements of A. Obviously, if this A is a imaginary or complex matrix, for example, if we have, let's say, A equal to 2 plus 3i, 4i, 0 and 6, then if this is A, we'll have to complex conjugate each of the elements. So 2 plus 3i conjugated will give you 2 minus 3i, 4i will give you minus 4i, 0 being real will give you the same, 6 being real will give you the same. So this is A conjugate. Obviously it has nothing to do with the size, right? Now what if we conjugate the matrix twice? Like if we had conjugated this z twice, we would have get conjugate of x minus I will become x plus iy. Similarly, if you conjugate a matrix twice, you'll get the matrix itself. And for overall, I'll write it here, multiplication being conjugated, it can be distributed without changing the or without reversing the order, right? Like for the case of transpose, AB transpose become B transpose into A transpose. Even in the case of inverse, we'll change the order, but this is only complex conjugate in which the order doesn't change. AB ka overall conjugate is A conjugate into B conjugate, right? And like we know for a complex number, when is it possible that Z and Z conjugate are same? This is possible when it is real, and Z equal to minus Z conjugate, this is possible when it is purely imaginary or 0, right? Similarly, if we have A being equal to A conjugate, this means A is purely real matrix, and if A is equal to minus A conjugate, it is purely imaginary or maybe 0, right? It has to be purely imaginary or 0, because 0 has nothing to do with, like, the conjugate of 0 is, it's negative also, it's positive also, so we can consider in both the cases. Next is transpose conjugate of a matrix. So as the name suggests, we'll have to do the transpose also, we'll have to do the conjugate also. So does this order whether we do transpose first and then conjugate, or we do first conjugate and then order matter? The answer is no. It doesn't matter whether you find the transpose first or you find the conjugate first. So how to find it and what is the denotation, how to denote it? You can denote it as, generally denoted as like this, or maybe like this, or like this, or you can change the order also, right? Or maybe it might be written as A H. Generally they'll mention, if they are mentioning anything like this, you may forget or not, you may not be able to connect, so they'll mention transpose conjugate. So you don't have to remember this part, but that's it, you should know this, that's it. Basically now in general questions you may not mention it may not be mentioned. So what do you need to do? We need to find the transpose, then conjugate, or the conjugate and then transpose. So it is obtained by conjugating and transposing the matrix. We'll see how the order doesn't matter. Let's say we take an example, 2 plus 3i, 4i, 0 and 6. I think this was the previous one, maybe, I don't remember. If we transpose this first, if this is A, if we transpose this first, we'll get the row becomes column. The first column is 2 plus 3 and 0, so 2 plus 3i and 0, 4i and 6, right? And now if we conjugate it, A transpose conjugate, this becomes 2 minus 3i, 0 becomes still 0, 4i becomes minus 4i and 6 becomes 6. What about this? This is like if we are conjugating it first, A conjugate. So A conjugate is 2 minus 3i minus 4i, 0, 6. And if we transpose the conjugate, 2 minus 3i and minus 4i is the first row, so it becomes first column. 0, 6 are the second row, so it becomes second column. So you can say in both the cases, whether you are trying to do the conjugate first or transpose first, you'll get the same result, right? You'll get the same result. So what are the properties? Like I said, if you do the transpose twice, you get the same. If you conjugate twice, you get the same. So somewhere they are both independent, and if you transpose conjugate twice, then also you get the same, because transposing twice and then conjugating twice, same. Also, if you have to find transpose conjugate of sum, see, the transpose we have clearly said the sum of the transpose is same as transpose of the sum, and again the conjugate of sum is same as sum of the conjugate. So both are independent, and ultimately you can say the transpose conjugate of A plus B is same as sum of the transpose conjugate of A and transpose conjugate of B. for the case of product, the transpose conjugate of AB, the order changes or reverses, and we can write it transpose conjugate of B multiplied with transpose conjugate of A. So you have seen in the case of transpose we are changing the order. In case of transpose conjugate also we are changing the order. In case of complex conjugate we don't change the order. A B का conjugate remains as A conjugate into B conjugate, right?